Welcome back to elementary statistics. In this video, I want to talk about t-tests with independent samples. Previously, when we were talking about the z-test, we talked about the difference between one parameter hypothesis testing, where you were comparing an unknown mean using a sample estimate to a known population. We also talked about two-sample z-tests, where you were estimating the means of two different populations using two different samples and comparing them. We can do the same thing with the t-test. Although when we are working with the t-test, we can be a little bit more specific, and it allows us more precise hypothesis testing. In the usual idea of a two-parameter test, we are going to have a control group and an experimental group. We will take the control group and the experimental group from the same general population, so they have shared characteristics and they should be very similar before whatever we are doing. The control group will be given whatever the standard treatment is. The experimental group will be given whatever the new treatment is that we are trying to analyze. Then we will analyze that data on both of those groups and we'll compare them. That's known as independent sampling. The control group and the experimental group are different samples treated differently and compared at the end. Another way that you can look at some situations is a before and after approach. You can collect one sample, one representative group of the population. You can measure parameters or you can measure statistical data before you do anything. You can do whatever it is you are analyzing in this test, and then you can measure the same values after. When you do that, you have paired data. For each member of the sample, you have their before and their after data, and you can compare each of them. That's what's known as a dependent sample. We'll talk about how to deal with dependent samples in a future video. For right now, let's focus on independent samples. Get my head out of the way, and I want to use the z-test as an analogy. In the one sample z-test for hypothesis on means, we estimated that mu was equal to x bar plus or minus the z-score times sigma over the square root of n. In the two sample case, we estimated that 0 was the difference between x1 bar and x2 bar plus or minus the z-score times the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. We took this fraction, sigma over the square root of n, for each of the two samples. We squared them, added them together, and then took the square root. That's how we went from a one sample to a two sample situation. For the t-test, our one sample situation looked very similar. Mu equals x bar plus or minus t times s over the square root of n. And so I hope it is not much of a surprise that the two sample t-test is going to also look very similar to the two sample z-test. 0 equals x1 bar minus x2 bar plus or minus t times the square root of s1 squared over n1 plus s2 squared over n2. The one thing that we needed differently about the t-test compared to the z-test was our degrees of freedom, which in the one sample test was n minus 1. In the two sample test, things get a little bit messy. Because your two samples are different sizes, n1 minus 1 and n2 minus 1 will give you different degrees of freedom. In order to err on the side of caution, we take the smaller of these. If they are the same, if n is the same in both samples, this is really easy. If n is different, then we have a little bit more work to do. Again, very similar to the situation that we had previously. So let's go through a quick example. Let's take a two-tailed test with alpha equals 0.01. The null hypothesis is that mu1 is equal to mu2, and the alternative hypothesis is that mu1 is not equal to mu2, and we will rewrite those to get everything on one side. So we'll write that mu1 minus mu2 is equal to 0, or that mu1 minus mu2 is not equal to 0. Then we will collect our data. Our first sample will have 42 members. It will have a mean of 36, and it will have a standard deviation of 11.8. Our second sample will have 17 members. It will have an average of 32, and it will have a standard deviation of 9.5. In order to perform a t-test, we need a t-score. In order to have a t-score, we need to have our alpha, 0.01 in a two-tailed test in this case, and we need to have the degrees of freedom. The smaller of the sizes of the two samples is 17, and 17 minus 1 is 16. So we come to our table of t-scores. We look for degrees of freedom equals 16, which is this row right here. And we look for the column. Whoops, sorry about that. We look for the column where the two-tailed test has alpha 0.01, which is, come on, highlight one thing. This column. There it is. There's the one we're looking for. Everything is highlighting. It's really making a mess. I apologize. All right, so following row and column, here is the particular value we're looking at. T is 2.921. And that gives us enough information to come back to our page, write out the formula. We are testing to see if 0 is x bar 1 minus x bar 2, which is 36 minus 32, plus or minus our t-score, 2.921 times the square root of S1, 11.8 squared over N1, 42, plus S2, 9.5 squared over N2, 17. I will do this calculation in several steps. I think that's going to make it less likely that I make a mistake. 11.8 squared divided by 42, my calculator tells me is 3.315. 9.5 squared divided by 17, my calculator tells me is 5.309. That's still in the square root. That's still being multiplied by 2.921. And we're still looking at the difference of the means, which I'll calculate as well, as 4. Continuing onward, I can take 3.315 plus 5.309. I can take the square root of that value. I can multiply by 2.921, and all of that gives me 8.578. And so, at the lower extreme, 4 minus 8.578 comes out at negative 4.578. And at the upper end of the range, we get 12.578. And since we have a specific number 0 that we test for the hypothesis in these cases, we are going to accept the null hypothesis. There is no evidence of a difference between these population means alpha equals 0.01. All right, that's all I have on this one. Again, hopefully not too different from the Z test. So if you're already comfortable with that, there's not a lot going on here except the degrees of freedom and looking things up on a different table. Thank you as always for joining me. I'll see you next time.